Okay, guys, can you hear me? Doing a sound check, doing a visual check. Can you see the paper? Can you see the words on the paper? Anybody? Bueller. Okay, Lauren, thank you. Thank you, Ashley. Can you see the paper? Okay, great. So I hope you're all doing well. I miss you. I miss coming to school every day. Thanks, guys. I got it. Okay, so I know people are going to come in late or whatever. That's fine. And if you get this stuff, you don't even have to stay and watch. You can watch it later as a review if you like. But I'm going to go over, I went over all the feedback that you guys posted on SB, which is good. And I decided to start with the last place we left off with, which was slope fields and differential equations, because a lot of you put that on there. So we're going to go back over these two topics, and then you'll have some homework that'll open up in WebAssign later on. And I will take attendance based on, sorry, I just wanted to shut the door to avoid background noise. I will take attendance based off of this list or based off of your participation in WebAssign. Okay, so anyway, make sure you have that WebAssign account, because the first homework on slope fields and differential equations will be due by the start of the next class cycle. And P.S., somebody emailed me, they did their homework in their notebook, and that's great and all, but you need to submit it through WebAssign, because WebAssign is grading it, and then I'm transferring the grades into the grade book. Yes, Milana, the streams are automatically recorded. And when I'm done, it's got a process in YouTube, and it takes a little while, kind of like uploading a video, but maybe a little bit faster. So after, I would say, depending on the length of the live stream, after maybe 30 minutes, you'll see the video appear so you can go back and replay it. So are there any questions before we get started? Any concerns, questions? I see we're out of school until May 31st, so. All right, well, at any time during the lesson, if you have a question, just type it in. I'll be watching the feed as I talk and explain. Yes, the district posted, I don't know what you mean by hold up. Who is Robbery SS? Is that a student in my class? I'm sorry, May 1st, yeah, not May 31st, but you never know. So at the rate we're going, could be May 31st, but we'll see. Oh, Robin. Yeah. Okay. So let's get started. And if you have any questions during the lecture, then again, just type in your question and I will answer it. Okay. So we're going to talk about slope fields and differential equations. And I want you to remember, this is very important, that the derivative of a function gives you the slope of the function at a point, right? We all know this. So a differential equation is just an equation that contains expressions in which the derivative appears as a variable. And so I put some examples here. I know I've done these in class, but there's a derivative here, y prime equals x cubed, or y prime equals y, etc. Okay, so it's just an equation, and it contains expressions which the derivative appears as the variable. Okay, so the big idea is when you're dealing with these differential equations, what you're doing is you're finding the function whose derivative appears in the equation. All right, so let's look at a simple one, and then I'll make it a little bit easier even. So for instance, y prime equals x cubed, right? Remember, we want to change the notation to dy dx because eventually we're going to separate those variables, but that's later. So we're going to rewrite this or think of it as dy dx. Either notation means the same exact thing. And just remember that y prime or dy dx equals or means the slope. So when does the slope equal x cubed? Okay, so what we're doing is we're looking for a function whose slope at any point in the plane is equal to x cubed at that point. So if I were to draw to x cubed and choose a point, maybe when x is equal to 1, I might want to know the slope of the function at that point x equals to 1. So just using this x cubed here, if I choose just some random point, say 1, 2, well, I have slope equals x cubed. So the only thing I can plug in for x is a 1 because x is 1. So if I do that, I get 1 cubed, which is 1. So the slope of this curve at the point where x equals to 1 is 1. And if I choose some other point, say 3, 5, then again, I'm going to plug the 3 in for the x, and I'm going to cube it. So the slope would be 27. Really, really steep slope. Okay, so the y value here in this case is not going to influence the outcome because there is no y in here. There's only x's. Capiche? So if I keep choosing more and more random points and draw little tangent lines of the slope, then what I'm going to get is a picture of the function that has these slopes. Okay, so that's what the slope field does. It takes a bunch of slopes, and unfortunately we have this terrible program, and I'm going to look today for that old program I had, which was amazing compared to this kid who did this one. The one that I downloaded into your calculator was the only one I could find that would work in the TI-84CE. So I'm going to try and find another one. I'm still searching. But anyway, if we put that on our calculator can do like a zillion points, right? If we wanted it to. And eventually we would get an idea of what the curve looks like or what the picture is. So if you remember the circle, I'm going to just pop the book under here. But I have a new computer and the legs of the computer are a nightmare. So it's blocking. Let me just turn the camera. Okay. So the differential equation for this was negative x over y, and we drew a slope field in our calculators, and we got these circles. So the function that takes on these tangent lines at these various points is the equation of a circle, some circle, okay? So I just want you to keep that in mind when you're thinking about slope fields. They're direction vectors or fields, and they give us the direction that the curve is taking on or that the function is taking on. All right, so the slope field is just going to give you a picture of what that function looks like, okay? And it's tedious to do a lot of them, but AP is going to force you to do at least some. So we'll talk about that, doing it by hand. And then, of course, we have the TI-84. So I'm just going to pop this back under here real quick. And I know it comes in grainy because of the lighting. But if we hit the program key and we press 1 for slope field and enter, then, we get the mind of Mike, right? So just press enter again. And we're going to input, I'm going to do the circle. And the circle's differential equation is negative x divided by alpha y. And I'm going to hit enter. And then what I want to view is the slope field. So I'm going to press 3. And the little slope field is going to come up. And so what you can say to yourself is, when you look at that differential equation, negative x over y, you may have no idea that's going to be a circle. But if you graph the slope field, you say, oh, what I know is I might not know the exact equation of the circle because remember, there's infinitely many circles. So one of those circles is going to be a particular solution to the differential equation. But I know that it's the graph or the function is a circle. So x squared plus y squared equals 1 or something. Okay? Don't forget how to use your calculator. Okay, so let's move on to the next one. Are there any questions so far? Anybody have a question? No questions? Nobody? Nothing? All right, well, if you do, don't forget to type one in. Okay, so here's the easiest one, which is y prime equals x squared. Now you're going to be asked to do these by hand, all right? And again, I don't know how well you can see it. I guess it comes up pretty good. I just printed and taped a piece of slope field paper here, so it's just the plane with a bunch of dots. You wouldn't have that many on an AP exam. How do you get out of the program? Oh, yeah, thanks, Robin. So, yeah, so you see, here's my program, right? It tells you press enter. So if you press enter, you're out of the program. Let me fix this. Okay, so we're going to look at, graphing one by hand. So we have y prime equals to x squared. Again, you want to think of it as the slope equals x squared. So I just chose a bunch of points and I wrote them down. Now, I'm going to put over here y prime equals x squared. If I choose the point, say, -2, 0, well, that means there's no y in here, so that means the only thing I can plug in is the x coordinate, and if I square a negative, I get a positive, so -2 squared would give me a 4. So the slope at the point, -2, 0, so we go -2, 0 right here. The slope is 4. That's a really steep slope, so I'm just going to draw my line kind of like that. It's not quite a 0 slope, but it's really close. For the slope field program, it doesn't matter whether you're in degrees or radians. But yes, I am in degrees. But in calculus, you should always be in radians. And the reason I'm in degrees is because I taught pre-calculus yesterday. Okay, so I drew that little slope, right? And at -2, 1, again, all I can plug in is the -2 because there's only an x. So guess what? It's going to have the same slope. So what I know is that if there's no y's, so there's a y prime, but I'm talking about just a y. If there's no y's, then on this vertical line, all my slopes are going to be the same. So even though there's a million points on this little thing, okay, the grader is going to look to see, are they pretty consistent? They don't have to be exact, but pretty consistent. Likewise, if I go to -1, 0, I plug the -1 in, well, y prime is 1. So my slope here is a 1. And guess what? If I go to -1, 1, it's also going to be 1. If I go to -1, 2, it's also going to be 1. So again, I can just make these little slopes of about a 1. Okay, that's the slope of that little line. Oops. Yeah, they are all -1. Sorry. They should be +1. So change that. Okay, if I go to say 0, 0, well, if I plug a 0 in here, I get a 0, so my slope's 0. If I go to 0, 1, I'm plugging in a 0, I get a 0. So I don't even have to think about it. All the slopes vertically are going to be 0. And if I do enough of these, go to 1, 0, my slope will be 1. If I do enough of these, I'm going to start to see that pattern emerge. And with the few that you're going to graph for AP, you're not going to be able to really see a pattern by hand. It would take a lot of them to see those by hand. You would have to do something way bigger than this. But the idea is that you can draw a little line segment with roughly the slope of that line. Okay, over at 2, 0, which is down here, if I go to 2, 0, my slope is 4. You see what I did? Because I was writing this up fast. Bad. So my slope, again, is 4. So it's going to match this here. And in fact, it's probably going to be symmetric about the y-axis. So anyway, I would just make my slopes of 4 like such. Okay? Is everybody cool on graphing the little slope fields by hand? What do you mean, how would you know if the line is vertical or horizontal? You mean the line, you mean when I say vertically? Oh, I'm going to show you that. So, because there's no y value in the original differential equation. So let me get the book here, and let me get a pencil. Here's a pencil. I don't want to write in the book. Okay, so let me transfer to the book. Now look, here's a differential equation, y prime equals 1 minus y. You notice there's no x in there, right? So if I choose the point, say 0, 0, well, there's not an x in here for me to plug the 0 into. I can only plug the y coordinate 0 in for y. Well, what's 1 minus 0? It's 1. So at the point 0, 0, I'm going to have a slope of 1. Now let's try the point 0, 1. If I plug a 1 in here, I get 1 minus 1, which is 0. So my slope here would be 0. So on this vertical line, right, x equals to 0, they're not going to be the same. I'm doing one right now, Jalen. Well, the differential equation generates the slope field. This is a differential equation. I'm plugging points in, and I'm getting the slope of a line. If I get enough, if I can do many, many, many of these little tiny slopes, what happens is that a pattern appears, and the pattern is the picture of the function, excuse me, whose slopes look like this. So for example, back to the circle. Whatever the function is, I don't know the function exactly. I know it's a circle, so it's x squared plus y squared equals some radius squared. But what I know is that if I follow these little slope fields around, you see these little lines are tangent about the circle. And maybe if I choose this circle with radius 1, well then these little slopes are tangent to the circle. Correct. If the slope of the line is 0, it'll be horizontal. So that's not the same as when I was talking about vertical a minute ago. So what I was referring to, so you notice I'm working vertically on this, on this line, x equals 0. It's just this particular problem. Okay, so when we separate the x's and dx's and y's and dy's, when we separate the differential equation, then we integrate it. We find the original function. And that gives us the function who has tangent lines around it that look like the picture of the slope field. That's the relationship. So bear with me a second. So we plugged in a 0, 0. We chose the point 0, 0. We plugged in a 0 for y, and we got a slope of 1. And I drew that slope. You're not dealing with diagonal lines. Don't think about lines here. Okay. It's not about the lines. It's about the direction or the slope of the original function, which you don't know what it is, right? You look at this is a differential equation. It's not the original function. To find the original function, you would have to separate the variables and solve this. But without doing that, we can get a picture of what the original function looks like by choosing points and plug in any random point you want. This is just limited because it's a textbook. There are infinitely many of these points in space, so or in the plane. So you choose the points that they give you. So they're giving me all these dots represent the points that George Best wants me to do in the homework. So I'm going to choose the points that are given, 0, 0, 0, 1, 0, 2, and I want to see what happens. So let's just watch and see what happens. Remember, there's no x in here, okay? So at 0, 1, I'm plugging a 1 in here. I get 1 minus 1. That gives me a slope of 0, which is a horizontal tangent line. If I plug in 0, 2, well, if I plug a 2 in here, I get 1 minus 2, which is negative 1. So the slope for this point is going to be a segment that looks like it has a negative 1 slope. If I plug in 0, 3, well, that's 1 minus 3, which is negative 2. So what I need to do for the grader is, if this is negative 1, I need to make this one look a little steeper. They kind of look the same, but it's hard to do that. And if I choose 0, negative 1, well, now I've got 1 minus a negative 1, which is 2. So my slope down here would be a positive 2. Is everybody okay with that? And on this vertical line, the line x equals to 0, you notice none of the slopes are the same. I can't just go up and copy the same slope. Is that okay? Okay, now let me erase this. And let's do when x is equal to 1. So we're going to do 1, 0. Well, remember, there's no x in my differential equation, so I'm going to plug the y coordinate in for y. If I had both x and y here, I would plug both of those points in to see what the slope would be. So I'm plugging a 0 in. 1 minus 0 is 1, and so the slope here is going to be 1. Now, let me jump to 2, 0 and see what happens. If I plug the 0 in, I still get a slope of 1. So the point I'm trying to make is that when you have a differential equation with just an x in it, no y, then vertically they're all going to look the same, right? As is did in my picture here. There was just an x, there was no y to plug into, and so vertically at the line y equals to 1, that's a line, right? All my slopes were the same. They were all 1. At x equals to 2, all my slopes were 4, and so you know, I could just kind of copy them all up and down the line. In this case, there's no x in here. There's only a y. So I'm plugging in the y coordinates, and what's happening? Well, guess what? I know that this is going to be a slope of 1, and this is going to be a slope of 1. So when there's no x, then horizontally, the line y equals 0, the line y equals 1, the line y equals to 2, they're all going to be the same. So if I choose, say, the point 1, 1, I would expect it to be horizontal, right? A 0 slope. Well, if I plug the y coordinate in, I get 1 minus 1, which is 0. It is. So I don't even need to think about it. I know all the rest are going to have a 0 slope. What about this one? I don't need to choose points and plug it in. I know they're all going to have a slope of about negative 1. And over here, we're going to have a slope of, what was that, negative 2, right? So a little bit steeper. And then down here, I don't have to plug in any points because this had a slope of 1. So these will, or no, this one had a slope of 2, I think. So I'm just going to go like this. So no x, horizontally speaking, they're all going to be the same. No y on the vertical, they're all going to be the same, just like in this picture. Does that make sense to everybody? Now, Jalen asked if I could do number 5. And I want to do number 5, actually, because it contains an x and a y. When there's an x and a y, whatever point you're working with, you're going to plug both coordinates in, one for x and one for y. So this thing starts at the point 0, 1. So let's start with that point. This means I'm going to plug a 0 in for x and a 1 in for y. Well, if I plug a 0 in the numerator, I get 0. And if I plug a 1 down here, I get 0 over 1. So what's 0 over 1? It's 0. So the slope here would be 0. If I choose the point 0, 2, Well, I'm going to plug a 0 in here and a 2 in here. I'm still going to get 0. So remember that the only time a fraction is 0 is when its numerator is 0. So guess what? All of these are going to be 0 because I'm plugging a 0 in for x. Let's go to the next one. So let's do the point 1, 1. Well, if I'm plugging in 1, 1, what I'm going to have is 2 times 1 over 1, right? Which is 2. So my slope here is going to be a 2. So I'm going to try and make it steeper than a 1. If I plug in the point 1, 2, well, I'm going to have 2 times 1 over 2, and the 2's cancel, so I'm left with a slope of 1. So there's my slope of 1. If I plug in the point 1, 3, well, then I'm going to have 2 times 1, which is 2 in the numerator, over 3. So 2/3, right? Less than 1, but still positive. So that's going to be a little less steep. Yeah, and if they give you one where the answer is undefined, then all you have to do is make a straight up and down slope, right? That's undefined. Is that okay? So in other words, when I'm trying to graph a slope of 4, like I did over here, I'm trying to make it so, and I did a terrible job, but this would be undefined, let's say, and maybe this would be a slope of 4. It's really hard to see the difference. A slope of 4 is a big slope. So you just try and make it a little bit different than the undefined one, just to let the grader know. But yeah, sure, they could be undefined. So if they had included this point 0, 0, well, I can't use that point because that's a unique case, but if they would have included, say, 1, 0, that would be undefined, and I would have to go like that. So the function would just be undefined there. And in fact, that would be some kind of asymptote. Okay, let's do, 2/3. So let me get rid of this. So there's my 2/3. Okay, let's go to the next one. So let's try the point, 2, 1. So if I use the point 2, 1, I'm plugging a 2 in the numerator, so I have a 4 over 1. So my slope is 4. So that's a pretty steep slope. So I'm going to make that be the slope of that looks like 4. And if I do 2, 2, well, that's 4 over 2, which is 2. So I'm going to make this slope look steeper than 1, but smaller than 4. So maybe something like that. And if I do 2, 3, well, that's going to give me 4/3. That's a little bit bigger than 1. So again, that's something that's kind of hard to. So like this is a 1-ish. So maybe just a tad bigger than 1. And you would get the points for it. You guys okay with this? So if I have 2 variables in the mix, they're going to be all over the place. Okay, anything goes. But the important thing to remember is if you only have an x in your differential equation, then what you know is vertically, once you get 1, you just right up and down. They're all going to be the same. And if you only have a y in your differential equation, like this other example, then horizontally, you can just make them all the same. In other words, the slopes on this horizontal line are not the same as the slopes on those horizontal lines. So you'd have to find 1 on each one, but then you could just copy them all horizontally. Is that okay? Are we good with that? So again, in AP, you might get something like this one. Well, you could get any combination where there's just a y, just an x, or both. But I'm talking about on FRQs, they usually give you very small ones like this. So you'd have to fill in something about this size on the AP exam. All right, let's go to the next page. I did another one for x squared, but I don't think now you need to see that one. Okay, so I just started some. on that one. Okay, I made a note here, so if you play back the video, and looks like we're going out of, whoops, focus, there we go. If there's no y in the differential equation, the slopes are the same vertically, meaning on any given x equals line. If there's no x in the differential equation, then the slopes would be the same horizontally. Okay, and again, you can use your calculator to pop in any differential equation and see. And again, if we do infinitely many, or a huge, like if this whole paper were a slope field paper, dotted paper, you know, if I did the whole paper, I might get a good idea of what the function looks like, which is why we have our calculators. All right, the differential equation. Back to this again one more time. It's any equation that has a derivative in it, right? Y prime. We need to solve them for either a general solution or an exact solution. And you can only find the exact solution if you're given the initial condition. So they will tell you find the general solution. That means you'll probably have a plus c in there somewhere, or an a times e to the x type of thing. And if they want the exact solution, they're going to tell you, they're going to specifically state with an initial condition. So you'll see those two words, okay? The steps are pretty easy. Number one, you're given the differential equation, and you know, you want to write, a lot of times those differential equations are given to you as y prime, and if that's so, you want to rewrite it as dy dx, right? Then you're going to separate. So after you rewrite it in this form, then you're going to separate and put the y dy's on the left side of the equation and the x dx is on the right. After you do that, you're going to integrate both sides. Okay, remember you only do the plus c on the right-hand side of the equation, and then you're going to solve for y. Yes, Mahi, they would give you these types of problems for FRQs. They're frequently in an FRQ. Remember those weekly homework assignments? Well, you're still going to have them. It's just been put on hold a little bit while we do this, while we get used to this. So let's separate, let's solve some differential equations. So remember, if I put this into my calculator, it's going to give me a picture of a slope field that represents the picture, the pattern, right? Like negative x over y, right? If I put that in my calculator, sorry, work constantly beeping us. If I put this into my calculator, I'm going to get, like with the circle one, a pattern so that I can make sense of the original function. So with the circle one, I put, you know, negative x over y. I got these slope fields that look like circles on my screen. So I know, I might not know the exact function, but I know that the function is a circle of some radius r. Okay, so what we're going to do is we're actually going to find the general solution. So I'm giving you a differential equation, and it's the question is find the general solution. So first of all, I want to rewrite this as dy dx is equal to negative 2xy. And then at this point, I want to separate. I want to get the y dy's on one side and the x dx's on the other. So what I'm going to do is I'm going to divide both sides of this by 1 over y, right? If I divide both sides of this by y, I get 1 over y. Okay. And now I got to get the x's and the dx's all over to the other side. So I'm going to multiply both sides by dx. So I get 1 over y dy is equal to negative 2x dx. Okay, so I've separated my variables. And at this point, the rule is now we're going to integrate. So let's integrate both sides. And if I integrate 1 over y dy, well, that's the natural log. So remember, with the natural log, you have to include the absolute value. So ln absolute value of y is equal to, now if I integrate this, I'm going to have negative 2x squared over 2 plus c, right? And this is going to cancel, so I'd want to write it out in the simplified form. It's going to be negative x squared plus c. And because we're dealing with the natural log, we need to get rid of it to solve for y. So remember, the big idea or the goal when you're solving differential equations is you want to end up with y equals something. You want to solve for y. So what we're going to have to do here is we're going to have to exponentiate both sides. So we're going to e it, right? That's what you guys call it. We're going to e both sides. And remember that for this side here, this whole quantity, it's e raised to that entire quantity because you're going to have to use rules of exponents. I'm going to move this paper. I'm going to work over on this side now because I have another example below this. So what happens here? Well, e raised to the natural log, they cancel. So you're left with the absolute value of y is equal to, now this side is important because, again, when the exponents are added, it's because we have the same base, right? So we can rewrite this as e to the negative x squared times e to the c, and we're going to tell the grader, let a equal e to the c, because e is a number and c is a number, and so a number raised to another number gives you another number. So it's a constant, all right, or a constant multiple. And we're going to replace this with a. So over here, I'm going to say, and by the way, I'm going to take the y out of the absolute values because it's going to be positive anyway. So y is equal to a times e to the negative x squared. So I'm just replacing this, right? And I'm using the commutative property of multiplication where I'm putting the a in front of the e for etiquette purposes. And that's my general solution. Okay, now you don't see the plus c in there anymore, but it's there because it's part of a, all right? That's it. We've solved for y. We've got a general solution, and we're done. Any questions on what I just did there? No, you need to replace it with a. Remember, one of the important aspects of AP is that you're learning sophisticated mathematics and you're expected to demonstrate that you can use it. Now, I know you can all do that. I don't have a question about that, but you have to show these unknown people that, okay? And so what they expect you to do is to write with that level of sophistication. So you would never, ever leave it like this, ever. You have to change this to something like A, and A is generally what we use. Okay, so we don't add a plus C on the left side because of this reason. I mean, we do. So technically speaking, you're right. We would have ln absolute value of y plus c is equal to negative x squared plus c, right? Now look, this is some constant that may or may not be the same as this constant. So I'll call this C1 and C2. If I subtract from both sides, a constant plus a constant minus a constant times a constant, or a constant divided by another constant is still a constant. So we omit this here and we just put it over here. Does that make sense? Does that make sense, Zach? Okay. Let's do another one. Here's the other example I have. It's a little more complex, but still, I'm not giving you an initial condition anywhere, so you're just going to find the general solution. I am doing another practice one right now. This one already has the form dy dx, so I don't have to rewrite it. What I need to start with is separation of variables. So I need to get the y dy is on one side and the x dx is on the other. So I can multiply both sides by 2y cubed and multiply both sides by dx. and this is a quantity. Is that okay? Now my variables are separated, and so we're going to integrate, right? We're going to integrate both sides. And, you know, if you want to, you can pull the 2 out and write it as the integral of y cubed or whatever, but we know how to do this stuff in our heads now. So if I integrate the left side, I'm going to have 2y to the 4th over 4. And if I integrate the right-hand side, I'm going to have x cubed over 3 plus 4x plus c, right? And I'm going to simplify this. This is 1/4 y to the 4th is equal to 1/3 x cubed plus 4x plus c. Now look, there aren't any natural logs in here, so I'm not going to have to e both sides. I just have to get y by itself. And y is to the 4th power, no problem. The first thing I can do is, I can multiply. So remember, when you multiply by a reciprocal, you have to multiply both sides every single term. But rather than that, I'm going to do this. Is that okay? Because again, a constant times a constant is still a constant. It doesn't matter. What's 1/2? Oh. You're right. I get talking and you see, I cannot multitask like that. You're right. It's a half. Thank God for whiteout. 2, 2. Okay, so what do I have to do now to get y by itself? I just have to take the 4th root of both sides. So y is equal to the 4th root of this thing. And you would just leave it like that. And that would be acceptable. Is that okay? Yes, I fixed it. Are we good with this? Okay, let's do one with an initial condition. It's going to be very clear because they're going to give you a differential equation and it's going to say with initial condition or something like that. So let's rewrite dy dx is equal to x root y. Yeah, the A thing only happens when you're eing both sides. I'm going to separate the variables. So I'm going to have 1 over root y dy is equal to x dx. And I'm going to rewrite this further as y to the negative 1/2 dy is equal to x dx. Now we're going to integrate both sides. So let's do that. Well, if I integrate the left-hand side, remember when we integrate, we're adding 1. So I'm going to get y to the 1/2 over 1/2 is equal to x squared over 2 plus c. And y to the 1/2 over 1/2 is the same as 2y to the 1/2. And that equals 1/2 x squared plus c. So again, we want to get y by itself. And if you want to write that as 2 root y, that's fine too. So I'm going to go ahead and divide through both sides by the reciprocal. So we've got, root y is equal to 1/2. And you can distribute it if you want to, but I wouldn't. And remember, if you do decide to distribute it, you're gonna have 1/2 times c. It's just c. You can call it d if you want, meaning it's another number. It doesn't matter. And then at this point here, in order to get rid of the square root, I have to square both sides. So I would just say that this equals that. Are we good with this? Are there any questions so far? Anybody have a question on what I just did? How do I get 2y to the 1/2? Here, you mean, Linda? Okay. So look, I'm going to do this over to the side. We have y to the 1/2 divided by 1/2, right? That's equal to y to the 1/2. Change division bar to multiplication, and then we flip the denominator. So y to the 1/2 is root y times 2 is essentially what you've got, so it's 2 root y. Does that explain it? So, right, what Pranay's saying is rather than doing all this work, and why you didn't see it here is because all you're doing is flipping this and multiplying it to what's in the numerator is essentially how that works. Okay, good. Here's another one. And these are the types that AP likes to give you because they want to see your arithmetic skills, your algebra skills, pre-algebra skills. So what I want you to notice is this is y prime equals e to the x minus y. So this whole thing is an exponent here. And the question is, how would we rewrite that? Because I can't separate it like that, right? Well, what do we know? We know that a to the m times a to the n is equal to a to the m plus n, right? Rule of exponents. For when our bases are the same, then we can write one base and add the exponents. So for the difference, what we can have is we know that a to the m over a to the n is equal to a to the m minus n. So what we want to do is rewrite this. We're going to change this to dy dx, but we want to rewrite this as e to the x over e to the y. Now we can separate the variables. So I'm going to separate them. E to the y dy is equal to e to the x dx. Now this is a nice little problem because we know the antiderivative of e to the anything is the same, it's itself, right? So if we integrate both sides, we're going to have e to the y on the left is equal to e to the x plus c on the right. We have to solve for y. So how do we get rid of e to the y? Well, before when we had the natural log, we had to e it because e is the inverse, e-ing, I guess you could say, sticking with your lingo. So when we e both sides, the exponential e to the x undoes ln x, they're inverses. Okay, so if we're dealing with e and we're trying to figure out how to get that y out, all we have to do is take the natural log of both sides. I'm going to put that in parentheses. So the reason why is because the natural log of e is 1. You cannot ever forget that fact. ln e is equal to 1. So this becomes a 1. And the rules of exponents with logarithms is that you can bring the exponent down in the front. That's a logarithmic rule, right? So what we have is y ln e, and that's a 1, so that's going to go away, is equal to, you could do ln e to the x plus ln of c is just a constant. And guess what? I can bring this down. So we have y, those are going to cancel, is equal to x. Cool stuff, right? However, they gave us an initial condition. They want to find, in other words, they want you to find, what is this c? Well, if I go back up here and I say, I want to find c, I need to do it up here before I actually take the natural log of both sides. So I'm going to use the point 0, 0, and I'm going to use e to the y equals e to the x plus c. And I'm going to plug a 0 in for x and a 0 in for y and see what happens. So I get e to the 0 is equal to e to the 0 plus c. Well, what does c equal? If I subtract, so e to the 0 is 1. If I subtract 1 from both sides, I get that c is equal to 0. So it was a nice, simple little application of employing the initial condition to show you that if c is 0, you get y equals x plus 0 or y equals x. Cute stuff. Are we good with that problem? You're going to get some more practice in your web assigned homework. Any questions? Okay, so what I'm going to do then is I'm going to stop at this point, excuse me, because we've been on for about 51 minutes now. Like, can you plug it into y equals to x? No. The initial condition, so let me go back to that paper. The initial condition is given to you so you can find the constant of integration. So you don't plug that into, let me see if I can find a simple one in the book. Let me do one more before I close out. Initial conditions. Here's one. Let me just get a clean piece of paper. Okay, so suppose, so again, the initial condition is so that you can find that plus c or that constant. Can you plug it into y equals to x to find the c? Yeah, you could if you want to think about it that way. But let's look at something here. I think we did this one in class before we were all quarantined. X cubed dx, right? I'm going to integrate both sides. So I'm going to have ln y is equal to x to the 4 over 4 plus c, right? At this point here, it's even actually a good idea. But to go ahead and plug in that initial condition, I wanted one that was a little simpler. Without having to deal with logarithms. But anyway, I guess we'll keep working on this one. So at this point here, you could plug this in. So, when x is 0, y is 3, right? So I could do ln 3 is equal to 0 plus c. Well, c is equal to ln 3. Okay, so what my exact equation looks like at this point is ln y is equal to 1/4 x to the 4th plus ln 3. Remember, that's just some number. Okay, now I can exponentiate both sides and get y by itself, right? And I can let a equal to ln 3, but in this case, I don't even want to do that because I know what the number is, right? This would be e to the x to the 4th over 4th times e to the ln 3. Well, this is still some number. Okay, so at this point here is probably where they're going to ask you to find the c, to be quite honest with you. I'll pull some FRQs and show you. All right, so, I would say let a equal to, e to the ln 3. So y is equal to a e to the x 4 over 4 or something like that. Okay, that would be an exact solution. I wanted one that wasn't quite as messy to show you, but, they jump right in AP to the more difficult problems that they expect from you. So you guys think you can handle solving differential equations for your homework and looking at slope fields. Bueller, anybody? Any other questions? For the previous problem, would you do A equals ln C? So not this problem, the last problem, John Newell. Figures, every time I'm doing a live thing, the street sweeper or something has to come by. You might hear the dog bark because she hates the mailman and the street sweeper. Don't bark, don't bark. No, no bark. Okay, she's probably going to go into a barking frenzy, and I apologize in advance. So you're talking about this one, this problem, John Newell? So could you do, let me reread the question. A is equal to ln C. Yeah, sure. So here's the thing. Wait a minute, John Newell, hang on. Let me just relook at this again for a second. So this is, again, at this point, once we integrate, so over here, we're going to have e to the y is equal to e to the x plus c. This is not part of the exponent, so no, John Newell. I'm glad I looked at that again. No, this is not the same. This does not equal e to the x plus c as an exponent. Okay, this here you can write as e to the x times e to the c. So then you could do it. But in this case here, the plus c is independent of that exponent on e. Make sense? John Newell, does that make sense? Okay. So with that, I think I'm going to end. Give you guys a break to start on your homework. So the A thing. It's not an A thing. It's you guys with the word thing. The A thing does not happen for logs. Okay. So where's the one I had with the log? It does happen with the logs. So here was the first, I think the first example we did. Okay. The only way to get rid of the natural log is to exponentiate both sides. When I exponentiate the right-hand side, this whole quantity becomes a degree or a power. Okay. So this is e to the negative x, well, like I have down here, e to the negative x squared times e to the c. It's much different than if I do e to the x, ln, e to the x plus c. This is not part of the exponent. Do you see the difference? It's called replacing a constant with another representation of a constant. All right, you guys go try your homework. Okay, again, it's due at the start. It'll give you the due date. So once it's past the due date, you won't be able to get in to do it. So make sure you're at least working on some of it. Do the best you can. And then next time I see you, which will be Thursday, I can't keep track of the days anymore with all this time. It's just so weird. But on Thursday, you'll have the opportunity or before then to ask me questions. I think you'll all be okay with the homework, but You know, EDSB has really been having a lot of problems. It's really difficult to get in. I'm sure you all know that. So if you have a question, you can send a remind text to me because my phone dings every time one comes through. So um, yeah, replacing a constant with another constant, another representation of a constant. So let's be clear about that. um, so you can text me by remind, you know, if you get stuck. But what I think I'm going to do is you know, take a few minutes, just like I do at the start of every class when we're in school, and say, what are the homework questions, and go over those on the board. No, you can pause the homework and go back to it as long as it's finished by the due date. So you can, you know, just make sure you save your work. I think there might be a save button there, and make sure you submit it. Um, no, I'm not making a telegram. Right. Send Gage the assignments to. Oh, wait a minute. Does it say? Yeah, April 2nd. Today's the 31st. So you get 2 days. So just like you do in class, right? I assign you homework. You work on some in class. What you don't finish, you do at home. And then it's done by the next class session. So that way you can ask questions and I can answer them. How we always do it in class. Make sense? So are there any more questions before I log off? Anybody? Anything? All right, then I guess I'm going to conclude this lesson, this session, and I will see you all on Thursday. And again, if you have any questions, don't hesitate. All the questions need to go through EDSB. That way we have a record of them. Or Remind. You can do it on Remind too, because I do have a record of those. Don't hesitate to email me if you need help with something. I hope you all have a great rest of your day.